on or interested in mathematical modeling of infectious diseases and other threats to public health. Bienvenue à tous. La série de séminaires MFPH Next Generation est un événement pour les chercheurs en début de carrière, les modélisateurs juniors, les épidémiologistes travaillants intéressés par la modélisation mathématique des maladies infectieuses et d'autres menaces pour la santé publique. First of all, we wish to acknowledge this land on which the FEEDS Institute operates for thousands of years. It has been the traditional land of Huron-Wendat, Seneca, and Mississaugas of the Credit. Today, this meeting place is still the home to many indigenous people from across Turtle Island, and we are grateful to have the opportunity to work on this land. Premièrement, nous souhaitons reconnaître cette terre sur laquelle l'Institut FEEDS opère depuis des milliers d'années. C'est la terre traditionnelle des Huron-Wendat, des Sénèques, des Mississaugas. Aujourd'hui, ce lieu de rencontre abrite encore de nombreux peuples autochtones de toute Turtle Island et nous sommes reconnaissants d'avoir l'opportunité de travailler sur cette terre. So our guest today is Professor Woldegebriel Assefa. He's assistant professor at York University in the Department of Mathematics and Statistics. He holds a PhD in biomathematics from the University of Buea with the co-supervision from Lehigh University. And he was postdoctoral researcher fellow in mathematical models and methods in biosciences and bioengineering lab at the University of Pretoria, South Africa. He got his master's degree at African Institute for Mathematical Sciences in applied partial differential equations. His fields of research are mathematical immunology within and between host infectious disease modeling the impact of climate change on infectious disease dynamics, applied differential equations, viscosity solution of Hamilton-Jacobi equations, and application to control theory. Notre invité aujourd'hui, le professeur Gabriel Assefa, il est professeur adjoint à l'Université de York au département de mathématiques et de statistiques. Il est titulaire d'un doctorat en biomathématiques de l'Université de Buea avec une co-tutelle de l'Université de Lehigh. Il a été chercheur postdoctoral en modèles et méthodes mathématiques en laboratoire biosciences et bioingénierie à l'Université de Pretoria. En Afrique du Sud, il a obtenu son master à l'Institut africain des sciences mathématiques aux équations dérivées partielles appliquées. Ses domaines de recherche sont l'immunologie mathématique, la modélisation des maladies infectieuses au sein et entre les hôtes, la modélisation d'impact changement climatique sur la dynamique des maladies infectieuses, les équations différentielles appliquées, les solutions de viscosité des équations d'Hamilton-Jacobi et leur application à la théorie de contrôle. His talk will be today on fractional differential equation models for disease transmission dynamics, Hepatitis B virus with 2H structures as an example. Sa présentation aujourd'hui portera sur un modèle d'équation différentielle fractionnaire pour la dynamique de transmission des maladies virus de l'hépatite B avec structure à 2H comme exemple. Thank you, Professor, for your presentation today, and we are looking forward to hear from you. The floor is yours.
All right, thank you for the long and nice introduction. And okay, so I have to start, right? I probably have to share my screen. And okay, sharing is here. So let me try if it is working. Can you see my screen?
Yeah.
Okay, excellent. Thank you very much. Thank you, everyone, for joining us today for this talk as part of the next generation seminar of the Mathematics for Public Health, which is hosted by the FEEDS Institute. And hopefully everyone has a good day or maybe good evening, depending on the time zone, or good morning, probably. And today I'm going to talk about the use of fractional order derivatives for modeling disease dynamics. Particularly, I will consider the Hepatitis B virus with 2H structure as an example. I am Woldegebriel Assefa, and I am an assistant professor at the Department of Mathematics Statistics at York University. It has been now more than 1 year and a half, almost 18 months since I joined York University. And my today's talk will start with a general brief introduction of what is fractional calculus? I will introduce briefly the mathematical theory and result of fractional calculus, which is fractional order derivatives and fractional order integrals. Then I will also list some applications of fractional calculus towards science and engineering, modeling in chemistry, biology, physics, and other phenomena. And then I will consider fractional order model of hepatitis B virus as infectious disease modeling, where I will try to consider from the deterministic ODE model. Then I will extend this one to the fractional order models. If time permits, I will also go with some of the qualitative analysis of the fractional order model. And mainly, I will show you some numerical analysis results where we try to consider the effect of order. That's the effect of order derivative. In other words, the effect of memory on the dynamics of hepatitis B virus by considering, for example, varying the vaccination of newborn and varying vaccination rates of adults. And again, we will also consider how does the memory, or that means the order of derivative, affects when we vary other control parameters. To begin with, I will start with a general introduction to fractional calculus. What is fractional calculus as a field? Of course, fractional calculus is part of applied and pure mathematics. And as a simple definition or simple introduction, fractional calculus is simply the field of applied on pure mathematics that studies the fractional order derivatives and the fractional order integrals. What do you mean by this one? Usually in the when we join university or the end of high school, we take course on calculus in high school. Probably as part of our undergraduate study, we take courses such as calculus 1, calculus 2, or 3, depending on the type of the department. But in that case, we have these derivatives. I will call them here traditional derivatives, or I'll call that one a fractional calculus, where we have positive integer derivatives. But the fractional calculus extends those study or these concepts to non-integer order derivatives for any real number and complex number. Okay, let's start. Let's go back to calculus 1. In calculus 1, we have derivative. One chapter is about derivatives of functions. In that case, we have only positive integral order derivatives of functions. In that case, let me consider my function is f of x, where the independent variable is x in this case. Then we have the first order derivative, which can be either donated using the Leibniz donation, which is dy by dx, or can be donated using the prime donation, or we call it Lagrange notation, which is f prime of x. Then this is, if we have a function, for example, f of x is x squared, let's go, f of x is x to the power of 6, then the first order derivative will be 6 times x to the power of 5. Then we can continue with the second order derivative, all third order derivative up to the nth order derivative. These ones are ordinary derivatives. That's none. This is positive integer derivatives. So for example, in that case, we can define and compute the derivatives of functions when n is positive integer. And of course, we call those notations, as I tried to introduce, if we have the Leibniz notation or the D notation, which we can use D capital is to donate the derivative with respect to the independent variable. Similarly, we can talk about integrals, integral calculus. Then the next chapter in calculus 1 is integral calculus, where we try to familiarize ourselves with antiderivatives and then with indefinite and definite integrals. If we have a function f of t, for example, then I can donate the integral of the function from point A to some demu variable t, which is donated by I of this one. Then we can find the integrals. If we have, for example, sine of x, then the integral of sine of x is cosine of x. Or if we have x to the power of 6, then the integral of x to the power of 6 is 1 over 7 times x to the power of 7, x to the power of 7. These ones are in the sense of classical calculus. But the problem is, what happens if we have fractional order derivatives? For example, in this case, I have the nth order derivative of f with respect to x, where n is positive integer. What if n is equal to 1 over 2? What if n is any fraction? How do we find the derivatives of fractional order derivative? That is the question that led to the development of fractional calculus. I will show you in the next slide how this came up when there was a discussion between two mathematicians named L'Hopital and Leibniz. And we know already Leibniz, I introduced Leibniz is one of the pioneers for the development and innovation of calculus, especially introduces the notations of and the definitions of derivatives. Then Leibniz published a paper on some results related with derivatives and calculus. Then L'Hopital, some of us who took calculus 1 know L'Hopital. For example, when we compute limits we have the L'Hopital's rule. In the case when we have the limit of the function is infinity over infinity or 0 over 0, then we use the L'Hopital's rule. So the mathematician L'Hopital asked Leibniz, what if the order is n equal to 1 over 2? Then Leibniz replied by saying it will lead to a paradox from which one day useful consequences will be drawn. This was the birth of fractional calculus. And this letter was written in 1695, and dated September 30th, 1695. And this is considered as the birth date of fractional calculus. Then after this one, many mathematicians, physicists and engineers has contributed to the development and innovation of many results under fractional calculus. And later on, many others has tried to use the concepts of fractional calculus to apply to different problems, real-world problems in physics, engineering, and other biological phenomena. So that's how the fractional calculus came up with the question of L'Hopital asking Leibniz that what happens if your derivative is a fraction? Okay, so of course the history of fractional calculus is big. There are a lot of literatures related to the development of the concept of fractional calculus starting from 1695. I will show you a few of them here. For example, in the early 18th and 19th century, there was a lot of scientists who has contributed to the development of fractional calculus. To mention a few of them, we can see Leibniz, of course, then Euler, Lagrange, Laplace, Fourier, Abel, Livigny, Riemann, and others has contributed to the development of the mathematical theory and results related with fractional calculus. But during the 20th century, the research on or toward the fractional calculus was very slow, and somehow it was dormant until the 1985. And after 1985, other mathematicians has showed interest in the use of fractional calculus for applications. Particularly, we can mention in the recent years, probably in the past 10 or 15, 20 years, there were a modern form of definition of fractional order derivatives and fractional order integrals, commonly used for applications in epidemiological modeling, fluid dynamics, and other problems in engineering and science. To mention some of the modern definitions of fractional order and fractional integrals are, we have the Riemann-Liouville derivative, we have the Caputo derivative of fractional order, and we have the Caputo-Labrinzo derivative, we have the Antangana derivative, and others. Why I mention this one is that those ones are the commonly used in infectious disease modeling. And I will show you later on the definitions of each of those ones. But let's go back again to the first definition. How do we motivate the fractional order integral of a function? We'll consider instead of n, when we consider n a positive integer, we have the classical or the derivative and integrals of functions that we learn in Calculus 1 in undergraduate program. In this case, we are considering order derivatives of alpha, where alpha is positive, alpha can be negative. We can extend this definition to when alpha is any number. So what we have is, we start with the first one is, we know that from calculus, we have the first integral here from a to t, which is the definite integral, where we apply fundamental theorem of calculus, and I will denote this one is by I of t or j of t. Some researchers use j, others use I. Then we know that in calculus 2 or calculus 3, we have double integral, triple integral, or multiple integral. That means integrating a function twice, 3 times, and n times. In that case, we have this one is, for example, I2 represents the second double integral. Then we have n, this is multiple integral. And we can find the integrals in this one. Using induction, this can be extended to a general formula, which was developed by Cauchy, and it's given using factorials of positive integers. So the nth integral of a function f of t, when integrated this one n times with respect to tau from a to t, is given by this formula, which is 1 over n minus 1 factorial. We know the usual factorial for positive integer. Remember that n in this case is positive integer, n minus 1 is also a positive integer. Then we have the integral from a to t of t minus tau, where tau in this case is a Dumi variable. Then we have n minus 1 of t d tau. But the question is, what if n is not a positive integer? what if n is generalized to any number alpha? This is a question that we have to answer using of course, several researchers has tried to answer this one, and the different definitions or different forms of the definition of fractional order integrals and fractional order derivatives have evolved throughout the past century, and mostly some of the used definitions are those ones defined by Riemann and Liouville, and the other one is the Caputo derivative, and of course there are others. So I'm going to show you the fractional integral order derivative in the sense of Riemann-Liouville, and then I'm going to show you the fractional order derivative in the sense of Riemann-Liouville. Then I will continue analogically to the Caputo sense. Let's start, for example, with the fractional order integral in the sense of Riemann-Liouville. So what we have is, in order to generalize, let's go back here. In order to generalize this one to any n, which n can be alpha, which is any real number, what we do is, we know that factorials are defined only for positive integers. But an extension of factorial is the gamma function, which is defined for any complex number. So in order to extend this definition to any order alpha, we use the concept of the definition of gamma function. So we start with the definition of gamma function. We know that for any complex number z, the gamma function of z is defined by this improper integral, provided that its limit, this improper integral converges. And one fundamental property is, particularly if z is positive integer, then the gamma of n is simply the factorial of n minus 1. And for any positive complex number z, gamma of z plus 1 is given by this property, z times gamma of z. These are fundamental properties of the gamma function. Then using this gamma function, we can extend the Cauchy formula to any number alpha. And what we have in this case is the fractional integral of order alpha in the sense of Riemann-Liouville is given by this integral. So instead of having 1 over n minus 1 factorial, we have here is 1 over gamma gamma function of alpha. Then we have the integral here, which is the integral from a to t. Then t, this is similar, replacing n by alpha. Except that here we do have, instead of having 1 over n minus factorial, this is 1 over gamma of alpha. And here we have alpha. And in this case, we define, for example, when alpha is 0, this is a function. That means the zeros integral is the original function by itself. Same thing is the zeros derivative with this one. Okay. Then if this is the fractional integral of order alpha in the sense of Riemann-Liouville, then what will be the fractional derivative instead of integral? Okay. The next one is now, I want to move on for the fractional order derivative. The definition of the fractional integral is straightforward, as we have seen earlier. It is simply the extension of the Cauchy formula for multiple integral by using gamma function. Now, in order to define the fractional order derivative, you need this more careful analysis, and it's not straightforward like the case of fractional integral. For example, in the sense of Riemann-Liouville, the fractional order derivative function f is given by the nth order derivative of the fractional integral, which is given by 1 over gamma of n minus alpha. Then we have the nth order derivative of this integral, where n is given by, we have this is the greatest positive integer less than or equal to alpha plus n, or we can consider this one is alpha lies between n minus 1 and n. So this is the definition of fractional order derivative, where alpha in this case can be a fraction in the sense of Riemann and Liouville. And in this case, we can just simply say that the fractional order derivative in the sense of Riemann and Liouville is simply the left inverse to the corresponding fractional integral in the sense of Riemann and Liouville. And in this case, if you consider positive integer m instead of alpha, where alpha lies between m minus 1 and m, then we can define the fractional order derivative of alpha is simply equal to this one, which is the m's derivative of the fractional integral of f of t. And this is defined by, if alpha is a positive integer, then the fractional derivative will reduce to the classical derivative. That is the traditional derivative that we know in calculus 1 and calculus 2, which is given in this case. But in the case where alpha is a number between m minus 1 and m, then we have the fractional order derivative is given by the derivative of this expression. That's how it is defined. Then the next one is, I want to show you that some examples. How do we define, for example, particularly if we have the power function, t to the power of mu, in this case, mu is a number. In the classical sense, then the derivative of t to the power of mu will be mu times t to the power of mu minus 1. If you continue with second order derivative, then it will be mu times mu minus 1 to the power of mu minus 2. It continues like this one. And we can we can use induction in order to find the nth order derivative of t to the power of mu when we have in the classical sense. But let's try to see this one in the fractional sense. This is simply given by the fractional order derivative, and it is given by this expression. If you use the formula, then it finally reduces into the gamma function of mu plus n over gamma function of mu minus alpha plus n, then t to the power of mu minus alpha, where alpha is the fractional order derivative and mu is the power of t in this case. So what we have is, in this case, is let's take simple examples. I took this one directly from the following reference, which I'm going to show you here. I just copied this one directly from this reference. And let's start particularly, suppose alpha is 1/2, half. And we have t to the power, mu is also half. So what is the fractional order derivative of t to the power of half when alpha is again half? This is simply, if you put it, mu is half here, then mu is half again here, alpha is half again here, then this will reduce simply the gamma of 1 plus 0.5, and this is equal to gamma of 1.5, which is defined using the definition of the gamma function, which can be computed. But instead of t to the power of n, let's take, for example, t to the power of 1. Mu is 1, and alpha is half. Then we have, this is the fractional derivative of t to the power of 1 when alpha is equal to 1/2 is simply given by this one. If you come up with this expression, replace mu by 1 and alpha is by 0.5, then you come up with this one. This is what it's telling us in this case is, in the case of classical derivative, if we have the derivative t, for example, the first order derivative of t is 1, second order derivative of t is 0, and it continues, which is different in the case of the fractional derivative in the sense of Riemann-Liouville. Let's take, for example, a constant 1. What is the fractional order derivative of 1? In the sense of Riemann, this is equal to 1/square root of pi times t. But remember that in the classical sense, the derivative of a constant is always 0. The derivative of 1 is 0 in the case of classical derivative. But in this case, the fractional order derivative, when alpha is equal to 1/2, the derivative of 1 is given by this one. Okay. But generally, we can generalize this one. If you see here, the fractional derivative of 1 with order alpha is given by t to the power of minus alpha over gamma 1 minus alpha. Particularly when alpha is 1/2, then it reduces to this expression. Oh, that's what we have. Okay, which is different from the case of classical derivative. All this, what I have showed you so far is fractional integral of order alpha and fractional derivative of order alpha in the sense of Riemann and Liouville. The next slides, I will now move on another approach of defining fractional order derivatives and fractional order integrals in the sense of Caputo. In this case, what do we have in the previous case? Let's go back here. I want to show you something. So what he's telling us here is that, first of all, you make the integration, then you have the derivative. Then in the sense of Caputo, it will be the reverse. You first of all have the derivatives, then you integrate. Okay, here is where it is. In the case of fractional order integral, in the sense of Caputo, it is the same. But in the case of Caputo's fractional derivative of order alpha, what we have is here, we have the same expression 1 over the gamma function of n minus alpha. Then we have the integral of the nth order derivative of the function. Then we have this same expression here. Okay, so what is the difference between the Caputo fractional order derivative of order alpha and Riemann-Liouville fractional order derivative of order alpha is that one of the differences is that in the case of Caputo, we first of all have the nth order derivative, then we integrate. But in the case of Riemann and Liouville, we first of all integrate, then we have the nth order derivative. Another advantage of this one is that in the case of, as we have seen, in the case of Riemann-Liouville, the fractional order derivative of a constant is not 0. But this definition gives us the fractional order of a constant is 0. This is one of the advantages. Okay. Another advantage is when we use fractional calculus in the application of modeling physical and biological phenomena. Then in the case of if we use the Caputo fractional order derivative, and when you try to solve these systems of differential equations using the Caputo derivative, it is not necessarily required to define the fractional order initial conditions. So when you define initial conditions, then it's not necessarily required to define the initial conditions to have fractional orders. Okay, that's why most of the epidemiological models that use fractional order considers fractional derivative in the sense of Caputo. This is a summary. If you consider, for example, n as a particular case, n equal to 1, then the fractional order derivative of order alpha, when alpha between 0 and 1 can be summarized in this form. This is in the sense of Riemann-Liouville. As you can see that here we have this expression. Then in the sense of, if you consider this is the integral, if you consider the derivative now in the sense of Riemann-Liouville, then we have this is the derivative, then the integral. We first of all integrate, then we have the derivative. But in the sense of Caputo, we first of all differentiate, then we integrate. This is the difference, particularly in the case when n is equal, fixed to be 1, and alpha is between 0 and 1. Having defined all these concepts, then the next thing is that what does the literature tell us about the solving fractional order derivatives? When I say fractional order derivatives, we still have fractional order PDEs, and of course, in this case, we can extend in different ways. Like we have, for example, differential equations. We have ordinary differential equations, partial differential equations, and continuous. Then we have fractional differential equations. So in the case of analytic methods, of course, there is adequate theoretical results on the existence and uniqueness of solutions for fractional order differential equations. But the problem is we don't have adequate enough analytic methods in order to solve fractional order differential equations. Rather, we rely on some numerical methods. Of course, there are several numerical methods that can be applied to solve fractional order differential equations or fractional order system of differential equations. Some of those methods are listed here. Of course, there are some analytic methods, including, for example, you can use called the Smoothie transform or the Laplace transform, and there is another one what they call is differential transform methods that can be used to find the analytic solutions of certain forms of fractional order differential equations. Okay, and there is another method what they call is the homotopy decomposition method. Homotopy decomposition method, which is mostly applied again for fractional order differential equations. The most important part is there are theoretical results that tells us that guarantees us the existence and uniqueness of solutions of ordinary or solutions of fractional differential equations. I'm sorry, I was teaching a course on ordinary and partial differential equations, and I have to apologize that I may frequently mistakenly call ordinary differential equations or partial differential equations. If I mention ordinary or partial during this talk, I meant fractional. Okay. So now, of course, we want to talk that once we have the theoretical results and existence and uniqueness and numerical analytic methods, then the next question is, where do we apply fractional calculus? That is, where do we apply fractional derivatives and fractional integrals? Are they applicable? Yes, the application of fractional calculus was not developed at the early development of fractional calculus. This is because it was complex at the beginning and it lacks some physical and geometric interpretation of fractional order derivatives and fractional integral derivatives. But later on, especially in the past decades, 1 or 2 decades, the fractional calculus has emerged as one of the most applicable results of applied mathematics in science, engineering, population dynamics, infectious disease modeling, and etc. And as you can see, for example, the main reason is because fractional order derivatives considers memory effects. This is because of the many dynamics in science and engineering depends on the previous history, and again, they depend also on the frequency and how they evolve. On the frequency, the history, and other phenomena. What I will call this one as simple term is memory effect. This is because the evolution and dynamics of several systems in biology, physics, chemistry, and other engineering and science problems have a memory effect. A memory in a system means that how much information the system carries from the previous and from the past. And also, it also considers the other influences such as the frequency or maybe the other properties related with the dynamics. And for example, if you consider the usual classical ODE and PDE models, they use to model the state of the system at each time, and they don't consider on the previous history of the system. It is more or less. And that is why we need fractional calculus in many applications. Okay. So I will show you some of these applications as the summary of what I have been trying to say is that fractional order derivatives, generally fractional calculus is applied because it precisely represents and reproduces the non-local frequency and history dependent of power law phenomenon, including many problems in engineering, science, biology, and physics, including infectious disease dynamics. So this is the key properties of fractional calculus, that because it considers one, the non-local properties of the dynamics, two, it considers the frequency of the phenomenon, three, it also considers the history-dependent properties of the phenomenon. This is the same for the case of diseases. If you have, for example, some types of infectious diseases, if individuals know that the history of a particular disease in their region or in their community, they may use different preventive measures, such as, for example, isolation of infected individuals, or they may consider vaccination at the early stage, or of course, they may consider other preventive measures. Of course, in the case of infectious disease modeling, how do you consider the fractional order? There are different ways. One way is you can consider some auxiliary parameters where they may depend on the previous history or the memory. Okay, of course, fractional calculus is also useful in stochastic processes, applicable in finance, in economics, risk management, and other phenomena. For example, when we consider finance and economics, there is a shock. That shock of the economics and finance can be modeled by using memory effect. It's not only those ones. We can consider different mechanical and electrical problems. We can consider fluid dynamics. If you search in the internet, you can see that the fluid equation is also extended to fractional order differential equations. And of course, we can also use fractional order derivatives on fractional integrals in the case of biosciences and medicine and other applications. Okay, this is what I can say here. Of course, as a particular case is, why do we consider fractional calculus in the case of disease modeling? In the previous slide, I showed you generally where do we use fractional, where and when do we use fractional calculus in science, engineering, and other phenomena, real world problems. Particularly, I want to talk about the disease modeling, infectious disease dynamics. Let's consider, for example, we have the deterministic modeling where we use the SIR or SEIR, and there are other extensions of those models by considering treatment, vaccination, socioeconomic factors, and others. But in that case, we use positive integer order derivatives. However, those models do not consider the time scale, because we have, for example, if you consider the first order derivative, you have the first order derivative d. For example, the derivative of f with respect, the derivative of y with respect to t, or second order derivative is the second order derivative of f with respect to t. This does not consider time scale, does not consider fractions of times. But if we have fractional order derivatives, then we have, for example, fractional order derivative of order alpha, where you have, in this case, is the derivative of order alpha with respect to t. In that case, we have dt, the power of alpha, which is telling us the time scale, fractional times. Another one is the usual modeling approach for infectious disease does not consider memory, does not consider how frequent is the disease appearing, and does not consider, for example, history-dependent properties. This is, in this case, when we do some prediction and forecasting, it may not tell us exact predictions, or does not give us good predictions. Nevertheless, if we consider fractional order derivatives, it considers all these properties that I mentioned earlier. It considers time scale, because it considers fractional derivative. It considers other non-local properties of the dynamics. It considers the frequency, and it considers previous history or previous properties of the dynamics. This is something that we have considered. Additionally, when when you use fractional order models to model disease dynamics, and when you try to fit into data, usually we have over parameterization, or we don't have perfect fitting. And if we have, for example, estimation of parameters, it does not give us a good estimation. Rather, it gives us some ranges. One of the advantages of fractional order is when you do data fitting, it gives better data fitting because it has one more degree of freedom, since we are considering fractional derivatives. Okay, so having this one, let me consider one simple example that I took from literature that I cited here. I'm going to consider first order derivative in the sense of classical derivatives. If consider, for example, alpha is 1, then what we have is the first order derivative of u. U is representing some phenomenon, some quantity. Then we have lambda times u is equal to 0. This is linear first order differential equation. If we assume that alpha is equal to 1, where lambda is some parameter and we are considering t is positive number. But if you have now alpha, which is fractional order derivative, then this will become now a fractional order differential equation, where we have the initial condition is here, u of 0 is equal to 1. We are considering fractional derivative in the sense of Caputo because the initial condition does not consider fractional orders. Okay, so if we try to solve this one, you can consider different values of alpha. In the first case, if alpha is equal to 1, then we have the classical first order linear differential equation. You solve it, the solution is simply u of t is exponential of lambda t, where lambda is the constant which is given here. And this is simply an exponential function. And if we plot this one, this is a decaying exponential function. But if you consider now alpha a fractional number less than 1, then the solution of this fractional order equation is given by this expression, which we have e. E is a function which is given by this one, and it is named after the two mathematicians called Mittag and Leffler. This is called Mittag and Leffler function. Like we have, for example, the exponential function, we have the logistic function, and this is a special type of function in the study of fractional calculus called Mittag and Leffler function. And this is a generalization of the usual exponential function by considering fractional orders. We know that the fractional, this is e to the power of z is exponential function. Depending the sign of z, it may be exponential growth or exponential decay. And if in power series or time series expansion, the e to the power of 0, e to the power of z is given by this expansion. But if you consider a general function of fractional order, then it yields this function, which is given by z to the power of k, the same expression in the denominator. Then we have gamma function of alpha k plus 1. But here we have factorial of k. So this is a generalization of the exponential function. And the solution of this differential equation when alpha is a fractional order between 0 and 1 is given by this expression. And if you see the graph of this one for different values of alpha, consider lambda is equal to 1. I fix lambda equal to 1. Then when alpha is equal to 1, then the solution of this differential equation is given by the exponential of t, which is given by here. When alpha is equal to 1, we have this function, which is showing us that the trend or the solution curve of this differential equation is decaying, but it decays very fast. But if you use fractional order derivatives, in this case, the solution of this differential equation is given by this function, which is the Mittag-Leffler function. And for different values of alpha, when we have alpha 0.75, then we have the solution curve, which the trend is still decaying, but it's not as much as fast as when you consider classical derivative. And you can see that how much this one is telling us is that the Momer effect or the varying the order of the derivative changes the frequency of decaying. This is what it's telling us. Okay, so I can show you another one is in the previous case we had alpha is between, okay, let me go here. Alpha is between 0 and 1. Let's make alpha is greater than 1 now. In the next case, the same differential equation, alpha is now greater than or equal to, there is a typo error, this must be greater than or equal to 1. Then what do we have? Since now in this case, this is alpha is greater than 1, we need any initial value problem. We need two initial conditions in this case. We have u of 0 is 1 and the derivative of 0 is equal to 1. That's why we consider in capital sense, because in this case, the initial condition considers the classical derivative. Does not consider the fractional order derivative. In this case, the same thing, if alpha is equal to 1, then we have the classical differential equation, ODE linear equation, first order, then we have the solution is exponential of this one. But if alpha is equal to 2, then still, this is ODE, second order derivative, linear second order differential equation, which is ODE, and the solution is the cosine of this one, which is an oscillation. But if alpha is fraction now, then we have fractional order derivative, and the solution is given by the Mittag-Leffler function, which shows a damping oscillation, which I'm going to show you graphically in this case. So what is telling us in this case is that, okay, when alpha is equal to 1, we have the exponential function, it directly decays to 0. There is no oscillation. When alpha is equal to 2, we have ODE, second order differential ODE equation, then it yields an oscillation, but the oscillation is periodic. Then you can see that this is a black one, which is periodic oscillation. But if alpha is fractional, or the derivative alpha is between 1 and 2, not included 1 and 2, then what happens? Still it is oscillation, but it's damping oscillation. As you can see here, for different values of alpha, when alpha is 1.2, I have this, so it is, the oscillation is down, now decaying, and damping, what we call is damping oscillation here. When alpha is equal to 1, then we have this one again. When alpha is 1.2, this is what is showing us. So what is telling us is that considering Montgomery effect changes the output, changes the prediction, because it considers previous history, it considers frequency property, it considers damping property, it considers also other properties of the dynamics. Okay, having said this one generally, let me move on to the next one, is about fractional order model for infectious disease modeling, where I will consider hepatitis B virus. I think the time is going faster, so I will just introduce what is hepatitis B infection, or generally hepatitis virus infection. Of course, hepatitis is simply the inflammation of the liver. Inflammation of the liver can be caused by a virus, or it can be caused by non-infectious agents such as heavy drinking, heavy smoking. But in the case of the inflammation of the liver, which is caused by a virus, we have the hepatitis B infection, which we call is hepatitis disease, which are caused by 5 types of strains of hepatitis virus, named as hepatitis A, hepatitis B virus, C virus, D virus, and E. And out of those, it's only hepatitis B and hepatitis C that can lead to chronic diseases, and they are the ones which causes several infections and diseases every year. Particularly, I'm going to consider about the hepatitis B virus. There are the epidemiological characteristics of hepatitis B virus includes, we have some of them are, we have effective vaccination, and another property of hepatitis B disease, which is caused by the hepatitis B virus, is that about 2 from 3 people which have hepatitis B do not know they are infected until they get testing and treatment. And the other problem is it causes the liver to have cancer and leads to other types of diseases, including liver cancer and others. Of course, another problem is it leads to lifelong or chronic condition, and the different types of transmission means includes blood transfusion, semen during sexual interaction, or other types of blood and body fluids. Of course, there is also a vertical transmission during birth from mother to child. Having considered those epidemiological modeling, I'm going to show you, I think what we did is we consider fractional order model that models the hepatitis B virus dynamics, where we use the fractional order derivative in the sense of Caputo. And the model variables that we consider is we have 2 age structure, we have children and adult. Subscript C indicates for children and A indicates for adult. And in this case, we have, for example, susceptible children. We have infants which are vaccinated immediately after birth. And then we have the infectious compartment for the infectious, and we have the susceptible exposed, and we have the infectious compartment for the adults, which we have chronically, acutely infected and chronically infected adults. And we have the recovered adults. Having considered this one, I'm not going to go with the details of the assumptions. This is a deterministic model where we have the ODE model. Then having this one where in this case, omega is vaccination for newly born individuals, and we have another vaccination for adults is P, and then we have another vaccination is V for children. Having considered this one, of course, these are some of the main parameters as you can see here. We have, for example, omega is in fact vaccination coverage immediately after birth. Then we have P is adult vaccination coverage. Then we have male is maturation to adult after 14 years of age. And we have V is another vaccination coverage in children. And we have again, here what we have is 1/k, which is the probability that disease is transmitted to newborn at birth. And there are other parameters that the usual parameters we considered here. Having this one, then the next thing is how do we consider a fractional order model? And what we did is, in order to include the effect of memory, or in order to include fractional order derivatives, we rewrite the right-hand side of the previous equation, this one. The right-hand side equation is written using integral differential equations, which I am going to show you here. So the right-hand side is written in terms of integrals in the following form, where delta 1 is expressed by the gamma function, as you can see here, and where we have alpha is a number, we consider alpha between 0 and 1, and gamma represents the gamma function. And in this case, if you observe now, if you replace back, if you substitute back delta 1 in these expressions, we come up with these expressions on the right-hand side, and the right-hand side expressions are simply the fractional order integrals in the sense of fractional order derivatives in the sense of Caputo, as I can show you, because remember that the fractional order derivative in the sense of Caputo is given by this one, then you have 1/this one, and this expression is simply what is written in this case. So considering this definition, the right-hand side expressions can be transformed into the Caputo derivative. As you can see here, we have the fractional order ODE model for the hepatitis B virus that we consider. I don't want to go to the details. I see that the time is a little bit well, so I'll start with some of the numerical solutions. Of course, I jumped now the analytic solution because the analytic properties, and of course, I'm not going to go with the stability analysis because we have computed the reproduction number for the fractional order model. We also computed the disease-free equilibrium. We try to show the local stability analysis by using the fractional form of the root Lewis stability condition. We also try to show the global stability analysis by defining the Lyapunov function for the fractional order model. And the next step was we try to use some numerical simulations in order to see how varying the effect of memory, that is varying the order of derivative, affects hepatitis B virus infected individuals for both children and adults. Then the next thing is also we try to fix now the order of the derivative and then we try to now vary the vaccination rate for at different cases, that is vaccination rate at newly born and vaccination of children and then vaccination of adults. And then we compare this one on the number of infected individuals by considering the order of the derivative, which is alpha in this case. So I'll show you the first one is that we have in this case, for example, this is the plot of the number of infected children by varying the order of derivative. And as you can see here, what we have is when alpha is equal to 1, then it shows that the number of infected individuals without memory is following this path, and it shows that the number of infected individuals at each time interval, at each time point, when we have classical is higher than the number of infected individuals when you consider fractional order at each time point. So as you can see, this is what we have. And you can see that as we increase, even as we decrease the fractional order derivative, then you can see that the curve or solution curve is following this path, which shows that the number of infected children is lower than when we consider higher fractional order derivatives. The next one is now what we did here is similarly, we varied the fractional order derivative, alpha to be 1 and 0.85 and 0.65. And now we try to see what happened with the number of chronically infected adults. In this case, what we can see is that the number of chronically infected adults increases initially. As you can see, when alpha equal to 1, it increases initially to, this is to move towards the point where there is intersection point as this one when we consider different values of alpha. And this is at the beginning is because movement from the infected children, because they infected children, they will grow and they move on to the age gap where we have adults. And another one is, but later on, what is happening is that we have, but through time, the number of chronically infected adults is becoming larger in the system without memory compared to when we consider in the presence of memory. Okay, then the next thing is what we consider is that effect of newborn vaccination after birth. So in this case, we have, for example, the order of fractional order derivative, and then we increase the rate of vaccination for newly born babies. And as you can see that when the vaccination rate increases, this is expected. And now the number of infected children also decreases through time, as you can see. Similarly, we have another case is now the same approach, but we have chronically infected adults, and the same case is here. So vaccinating is showing us that vaccinating newly born individuals is more effective than comparing vaccinating adults. Okay, and this is where it is showing here. We try to vary now. In this case, vaccinating adults, and of course, as you can see that what we have is the dynamics that we have observed here. We observe that increasing newborn vaccination decreases the number of chronically infected adults and the number of infected children than increasing children vaccination or increasing adult vaccination. Okay, so the same approach, this one is again, as we have observed here. I want to just summarize here in the next 30 seconds. So what we had was we proposed a fractional order model for hepatitis B virus transmission with two-edge structure under vaccination, and qualitative analysis of the fractional order model was performed, including we computed the reproduction number, fractional reproduction number. Then we used the fractional root here with stability condition in order to study the local stability condition for the disease-free equilibrium point. And then we moved on to the global stability condition of both the disease-free and endemic equilibrium from the fractional order model by constructing Lyapunov function. The next thing is the numerical simulation that I showed you a few seconds ago. Then what we did was we investigated the effect of memory, and by varying the order of fractional order derivatives, then we try to see also how the effect of varying newly born vaccination affects the dynamics of the hepatitis B virus. And as a general observation is that from this result that we observed, it is observed that the number of infective individuals decreases faster for the model with memory than for the model without memory. And thank you very much. And what we have is another conclusion is also comparing by fixing, for example, the memory fraction, considering fractional order, but fixing the memory. If you compare vaccinating newly born and vaccinating adults, it shows that vaccinating newly born is more important to control the hepatitis B virus transmission dynamics. Thank you very much. I really appreciate for joining us today, and thank you very much for the co-authors. Again, thank you very much for the hosts, and thank you everyone. And there are some of the references are included here. If there are some questions, I may take some questions. Thank you very much.
Thank you very much.